In this lesson, we're going to be looking at using tree diagrams in order to represent probability. And when we're using tree diagrams, this is predominantly for multi-step experiments. So we can use a tree diagram for two-step experiment. So it is interchangeable with tables, but it's also the method that we use for when we've got more than two steps. So our learning intention today is to use a tree diagram to represent outcomes of multi-step experiments and also to calculate their probabilities. So by the end of this lesson, you should be able to construct a tree diagram to show options where each step is equally likely. Okay, so that's the first type of tree diagram we'll look at. The second type is a probability tree diagram. So we draw a probability tree diagram where when each of the outcomes aren't equally likely, basically the difference between a probability tree diagram and a tree diagram is that we attach probabilities to each of the branches. And the final thing you should be able to do by the end of this lesson is to find probabilities using these diagrams. So when we're looking at multi-stage experiments, a tree diagram can be used to show all the different outcomes at each of those successive stages. So for this first example, the probability of having a boy or a girl is equally likely. A family has 3 children. Draw a tree diagram showing all the possible, I didn't finish that sentence, all the possible outcomes. So we've got 3 children, so the first child, so when we draw a tree diagram, we always start from a point and it's going to branch off. So the first branch, the first child could be a boy or a girl. Actually, let me use a bit of blue. Okay, so the first child could be a boy or a girl. When we get to the second child, if the first was a boy, the second one could be a boy or a girl again. If the first one was a girl, again we can have a boy or a girl. When we get to the third child, again, boy or a girl, boy or a girl, boy or a girl, boy or a girl. So that's all the different possible options that we can have. So sometimes you might write your outcomes at the end. So you might sort of like summarize what you've got. So if we look along this first branch, then we could have had a family of 3 boys. If we go along the second branch, so along here and then down that way, then we could have had 2 boys and then a girl. And then if we keep writing these out, boy, girl, boy, boy, girl, girl. We started with a girl and then have 2 boys, girl and then a boy and another girl. You could have had 2 girls and a boy, or you could have 3 girls as well. Okay, so those are the different outcomes, and basically it's just looking at along each of these branches in order to work out each of those outcomes. Now, because all of these outcomes are equally likely, then each of these are also equally likely. So we've got 8 different options here. So if we want to find probability, it's going to be looking at how many of these are favorable out of the total 8. So here's a couple of questions. Find the probability that the family has exactly 1 girl. So you go through, you're going to pick out all of the options where there's exactly 1 girl, and there's 3 of them. So that probability is going to be 3 out of 8. The second one, the probability that the family has at least 1 girl. Okay, so that means a minimum of 1 girl. So you could have 1 girl, which we've highlighted here, could have had 2 girls, or we could also have 3 girls. So the probability that we've got at least 1 girl is going to be 7 out of 8. And the last question, the family has at most 1 girl. So these are all terms that you will see a lot of in your probability. If I've got at most one girl, that means the maximum is one girl. So let me just wipe these. If the maximum is one girl, then I could have one girl, which is these ones, or I could have no girls, which is if we've got all boys. So if I want at most one girl, then you can see there's 4 options out of 8, which simplifies to give 1/2. So be very careful with these words, at least, at most, exactly. You will see these words a fair bit. Alright, so this was an example where all the outcomes were equally likely. We also have situations where not all the outcomes are equally likely, so that we will have different probabilities for each of those different outcomes. And this is an example of that. 3 red marbles and 5 blue marbles are placed in a bag. A marble is drawn and its color noted and returned to the bag before a second marble is drawn. Construct a tree diagram showing all the possible results. So when we go to pick our marble, our first marble could have been red or blue. And then the second marble could also be red or blue. So that's sort of what our diagram's going to look like. But you can see we've got a different number of red and blue marbles. So what we do here is we write the probability along the branch. So the chance that we're going to get a red marble the first time is going to be the 3 out of 8. So we're going to put 3 out of 8 here. So the probability of getting a blue marble is going to be 5 out of 8. Now, after we've done our first drawing, we looked at the marble, we said, okay, it's a red marble. What we then did was we put it back into the bag before we picked out a new one. So what that means is when I go to pick out my second marble, I'm going to have exactly the same probability. Because I put the marble back in, I'm still picking from the total of those 8 marbles, and I'm just going to randomly take one out. So that means we're going to have 3 out of 8 and 5 out of 8 here. If I picked a blue one, again, it's been reset. So we've got 3 out of 8 and 5 out of 8. So what we need to do with these probabilities is if I want to look at the probability of getting 2 red marbles, what we need to do is move along this branch. And if we're moving along the branch, we're going to multiply those probabilities together. Okay, because we want to have this one as well as this one. So if we're adding, if both of them need to occur simultaneously, we're going to multiply them together. So if we look at these questions, find the probability that the marbles are the same color. Now there's 2 possible options for that. We could have had both of them red or both of them blue. So what we need to do is we need to look along this branch, calculate that probability, look along this branch and calculate this probability as well. And we want one of those options to occur. So what's going to happen is we're going to work out these by multiplying along the branch, but then because we want to have 2 separate branches, we add the branches together. So to work out the probability, same color, we're going to look at the probability of getting the 2 reds, which is 3 out of 8 times 3 out of 8, and we're going to add it to the probability of getting 2 blues, which is 5 out of 8 times 5 out of 8. And what we need to do is work that out, and that's going to be 17 over 32. So just put it in your calculator to work it out. So the probability that we're going to get 2 marbles that are exactly the same color is 17 out of 32. Okay, for the second question, find the probability that there is at least 1 red marble. So if we look at these options, at least 1 red, at least 1 red, at least 1 red. So these 3 options will have a minimum of 1 red marble, Or basically we want all the possible options except for when there's no red marble. So there's actually two methods that we can calculate this. One is to take these branches and add them together. The other one is using complementary events. So both of them are valid and they'll both give you the correct answer as well. It's really just about your perspective, which version you'd prefer. So if I want the probability at least one red, I could just add up those branches. So I'm going to go red, 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 blue, and blue, red. So when I add those up, it's 3 out of 8 times 3 out of 8 plus 3 out of 8 times 5 out of 8 plus 5 out of 8 plus 3 over 8, or times 3 over 8. So what we've got there is that first one is that first branch here. The second one is the red and the blue. And the third option is blue with red. If we go and calculate those, we add all of them together, we end up with 39 over 64. Now, if we use the other method, so if we use complementary, the probability at least one red is going to be 1 minus the probability of getting 2 blues. Okay, so if I want at least one red, the opposite, the complement of that, is to get no reds. Well, that's double blue. So that's going to be 1 minus 5 over 8 times 5 over 8. So that's this branch here. So if I take 1 minus 5 over 8 times 5 over 8, I do end up with 39 over 64. So I do have the exact same answer there. The last question, redraw the tree diagram assuming there is no replacement of the first marble. Okay, so when we replace and if we don't replace, the probabilities are going to be a little bit different. So just a reminder, we were starting with 3 red marbles and 5 blue marbles. And so if we draw our basic tree, you could either get a red or a blue. And then on your second draw, you're going to get a red or a blue as well. Now, with your first draw, it's still going to be the same as what we did before. The probability of getting a red is going to be 3 out of 8. The probability of getting a blue is 5 out of 8. But what changes is when we go to our second marble. So at the moment, what we've got is, we've got 3 red marbles and 5 blue marbles. 2, 3, 4, 5. If we follow this branch here, and I've taken a red marble out, I've taken out a red marble, and what that means is when I work out these probabilities, I'm working it out based on what I've got left over here right now. So if I've already picked a red marble, then I've only got 2 red marbles left, and it's out of a total of 7 marbles. If I'm looking at blue marbles, there's 5 of them, again out of 7. Now, if I take the same diagram, copy, if instead of taking out a red marble, I took out a blue marble first, then I'm going to get rid of that blue marble, and this is the bag that we're going to now work out our second lot of probability with. So now the probability of getting a red marble, we've still got 3 of them in there out of 7, and the blue marbles, we've got 4 out of 7. So what you can see is when there is no replacement, then when we have our starting branch, when we go to the next branch, the probabilities will actually change. And you'll need to be very careful with what's actually left over. So you might want to draw a little diagram, or if you're okay with just looking at the numbers and just writing out your numbers, that's okay too. So what you might want to do, rather than drawing those little diagrams, you might want to just up here, you write down If a red one's taken out, we've got 2 red and 5 blue left, or something like that. Something that's going to help you to remember that you've taken out something and what that thing that you've taken out is. So that's how we work with tree diagrams. So again, what we can do now is, because we've got our tree diagram, we could go and now answer these questions again based on this. I haven't asked you to, but we can then use this tree diagram to calculate further probabilities as well. So here's a couple of questions for you to have a go at, see how you go with it.